Okay. There we go. So we are starting a new unit today, and the unit is called Relations and Functions. And in fact, this is going to be the start of 3 units, actually, because 3 out of our units are in this strand of the curriculum. The first 2 units covered all of the algebra and number stuff, and now we're moving into another strand. Okay, it's like another branch of math within the curriculum called Relations and Functions. This one is an important one going forward into grade 11 and 12 math and beyond if you choose to go beyond. So I want to talk a little bit about it first. The first unit and the second unit, in my opinion, actually should just all be in one, but we split them up because otherwise it'd be a lot of information. But in the first unit, we basically talk about what is a relation? What is a function? What are some of the properties of these things? How do we represent them? How do we communicate about them? The second unit is about a specific type of relation and or function called a linear relation. Okay, so there will be quite a bit of crossover between the first 2 units at least, and then there's another one, a third unit at the end on linear systems, which we'll get into in a couple weeks from now. Okay, but I want to start out with this question: what's a relation? Now, you guys would have seen in grade 8 or 9 some information about relations. You may not remember, that's okay. But in fact, if you haven't seen them, you actually have experience with relations, even if you don't know you do. Okay? Does anyone remember what a relation is in the context of math? Or maybe give me an example of a relation. Probably looked at linear relations a little bit last year. Yes? No? Okay. I'm just going to dive in there. A relation is an association between 2 variables. Association or connection. Association. Sometimes it's actually between more than 2 variables, but that's not something that you really look at in high school math, so I'm not going to go there right now. Okay, so what are some examples? Well, there's tons of relations that exist in our world, and we study them all the time. There is a relation between the temperature outside and the day of the year. As we move further and further into winter, it gets colder and colder. And then as we move into spring, it gets warmer and warmer. And then summer is really warm. And then we go back into winter and it gets cold again, right? Now in Calgary, sometimes that relation is not super strong because we have Chinooks and crazy weather. But there is, in general, a connection or an association between the day of the year and the temperature outside. Okay, so these would be the 2 variables. One of them is the day of the year, one of them is the temperature outside. Okay, there's a relation between, for example, your height and your age. There's a connection there. There's a connection between like the price of oranges and the weather in Florida, right? If there's some sort of natural disaster and they can't grow oranges very well in Florida, then the price of oranges increases. So that's another, there's lots of economic connections as well. One of my favorites is there's a connection between the number of years of education and your income. Okay, and of course, there's always going to be anomalies. There's always people who, go to university for 15 years and make almost nothing, and there's people who never go to school and are billionaires. But in general, there's a very strong connection between how many years of education do you have and how much do you make at the end of the day. Anyone think of any other ones? Yep.
I guess skill over
totally. So your skill at a specific thing, like, I don't know, playing sports, practicing an instrument, increases over time. Absolutely. There is a connection between that. Okay? Yeah, so we study these all the time, and scientists in particular study these a lot, right? So if you've done a science experiment, which I know you all have, then you may have two variables where you're examining both of them at the same time. Usually one of them is the control or the independent variable, and one of them is dependent. And we track the data, and then oftentimes we'll graph it so that we can try and see, is there a connection here? That's what science really is about doing. We study data, we do different experiments or different studies, and then where the math comes in is we try to mathematically find some sort of connection between the things that we're studying so that we can predict about the future. Maybe we can make changes to some of the things that we're doing for better outcomes. Okay, so this is like a huge piece of math, science, research, all sorts of things. And in the field, this is what a lot of mathematicians do. A lot of mathematicians will work together with other scientists to support them in the math side of whatever they're trying to study. Okay. Now, in high school, we look in grade 10 at an overall, what are these things about? What are some of their properties? We're also going to look at functions, which are a very specific type of relation. And then as you move throughout the years of high school, you're going to look at different families of functions. Okay? And what I mean by a family of functions is their family of relations, I'm kind of using those words interchangeably right now, is that you'll look at a particular type of relation where a lot of the properties will behave in the same way. Okay? So I want to just go through some of those now. You don't need to memorize them or anything like that, but it's nice to get an overview. One of the ones we look at is linear. And graphically, when you graph these things, they form a line. That's why they're called linear. It has the word line in it, so they might look like that. This is the family of relations that we're going to study in grade 10. And this will basically be our second unit. We're going to look a little bit at linear relations this unit as well, but we're going to have a whole unit on just this. In grade 11, you will look at quadratic functions or relations. So those, I've spoken about those actually because that's why we learn how to factor ax squared plus bx plus c. When we graph y equals ax squared plus bx plus c, it makes that shape, which follows like projectile motion. So it might look like that. Or sometimes or not sometimes, I would say half the time, they can go the other way as well, open up or open down. So those are a very, very important type of relation because they can model so many things in the world. What else do we look at? In grade 11 and 20-1, you will also look at radical. Actually, no, this is in 30-1. Sorry, my bad. You look at radical relations. But we know what a radical is, right? So if you graph something like y equals the square root of x, it'll look like this. Okay. You will look at absolute value relations. Those would look something like this. What else? We spend a lot of time looking at trigonometric relations. And we will learn more about trigonometry at the end of this course. Those ones look like waves. Those are trigonometric. So they basically model anything that's cyclical. So actually I was talking about weather patterns and temperature. If you were to graph temperature throughout the year over several years, that's the pattern it would make, right? It's really hot in the summer, then it gets colder, colder, colder. This would be winter, warms up again that summer, and then it repeats as another year goes by. So this is trigonometric relation. Exponential, right? We've looked at y equals x squared, but if you have the variable in the exponent, then like y equals 2 to the x, for example, the variables in the exponent position, those look like this. Okay, you will look at rational relations, rational meaning that it's like a fraction. So something like y equals 1 over x, where the relation itself is a fraction and there's a variable in the denominator. That looks like this. Okay. So there's all of these different types, and then basically how one will differ than the other. You guys would have learned about transformations in previous years, right? So what is a transformation? You take something, you stretch it, you flip it, you move it up or down. That's basically what's going to change from one of these to the other within that specific family. But once you learn the basics about that family of relations, then you can work with a lot in terms of the different things that you might see that that relation could model. Okay, so basically we kind of go through these one at a time. In grade 10, we just look at this one. In grade 11, you'll look at quadratic, and if you're in 20-1, you'll also look at absolute value. In grade 12, you look at radical, exponential, trigonometric, and rational, both in 30-1 and 30-2. Okay, so you're going to kind of go through these one at a time and learn about the different properties. In this course, as I said, we only look at the linear ones, and then we're not going to like get into the weeds with all of the other ones. We're going to look at some basic things, but not much else. Okay? So that's like stuff to look forward to, I guess. Today, what I'd like to do today is look at, firstly, what is a relation? How are the different ways that we can represent relations, communicate about them? And how do we maybe go from one representation to another? What if we have a table of values and we want the graph? Or what if we have an equation, we want the graph? That kind of thing. Okay, so that's our goal for today. So we have already talked about this. What is a relation? It's an association between two variables. Okay. One thing I should also mention about variables, I spoke a little bit about this, is that typically, not always, but typically, when you look at two variables, one of them is dependent on the other. Okay, not always, but often. So as an example, and if you don't know which one it is, you can just put the two variables into this sentence and see which one makes more sense. The sentence is this. I'm going to use age and height as an example. Your age is dependent on your height, or your height is dependent on your age. Which one makes more sense? Yeah, the second one. It's not like when you get to be 5 foot tall, suddenly you're 14 years old, right? Your age doesn't depend on your height. It's the other way around. Your height depends on how old you are, because typically as you get older, up until a certain point, you continue to grow and you get taller and taller and taller. And then once you get a certain age, you don't grow anymore. And so your height rather, is just static until you get really old, and then your bones start to like disintegrate because of gravity, and then you start to shrink again. It's the full circle of life. But yeah, so that's one way to tell, is just say which of those two things makes more sense. Does your age depend on your height, or does your height depend on your age? If your height depends on your age, then height is dependent on age independent. So height would be the dependent variable, age would be the independent variable. Okay, so I'm going to speak to that as well, because it's important when we talk about representations of relations that we know what goes where. Okay, so I'm just going to start out with one example. We're going to look at 6 different representations. Here we don't actually know what the context is. We're just given 2 variables, x and y. Variables do not have to be x and y, though. They could be, like if I was talking about age and height, I'd probably use a and h, something like that. Or maybe time and height. Here, though, we have these variables x and y. When you have 2 variables and you're putting them into a table of values, I know that you guys have seen those before, the independent variable always goes on the left. Okay, so this guy will be your independent. And this one is your dependent. Okay. If you're in a situation where either one of them could be independent or independent because there's no sort of clear delineation between the two, then just pick one. Doesn't matter. Okay? But typically that's what we do. So this is a table of values. We could also represent that as a set of ordered pairs. Okay, so I know that you guys have seen ordered pairs before. These symbols here mean that this is a set of values. So if you want to show that all of these orders go together in one relation, then you need to put those curly brackets around your ordered pairs. Okay? Similarly to the table of values, your independent variable goes on the left of the ordered pairs or comes first, and then your dependent variable goes on the right. Okay? So there's actually not a big difference between a table of values and an ordered pair. Okay? Now graphically, when you are graphing these things, again, independent variable must go on a specific axis and the dependent variable goes on another axis. Does anyone know which is which? Yeah. Yeah, x, or the independent variable, goes horizontally. So this over here is the x-axis, and it's the independent variable. Okay, this over here is the y-axis, and this is the dependent. And the reason why it's really important to know that it's not just x and y, but dependent and independent, is because oftentimes you don't use those variables to describe a relation. If you're looking at distance and time, you may use d and t instead of x and y. And in fact, I think that would make a lot of sense. So how do we know which goes where? Which one's independent? The independent one always goes on the horizontal axis. And in fact, I prefer to talk about it as the horizontal axis and the vertical axis, as opposed to the x and y axis. Did you have a question?
Oh, I just remember something that we were talking about. Y to the sky and then x on the ground. I remember.
Y to the sky, x on the ground? Okay, yeah, if that helps, sure.
Memorize what axis we were.
Yep, you can do that. One thing, though, is just make sure that you know that if a relation uses different variables other than x and y, you should not be using those variables when you create your axes, right? The x-axis is not always the x-axis. It really depends on the variables that you're looking at within that relation. Okay? All right. So now, plotting these points, the first value represents where the point is horizontally. The second one represents where it is vertically. Okay? Right is positive, left is negative, up is positive, down is negative. So -2 is the first one, so we're going to go 2 to the left, and then 5 is the next one, so that's up 5. So that's our first point. And then 1, 2, so 1 to the right, 2 up. So the signs are very important too. Those tell us about direction. 4, -1, so 4 to the right, 1 down. And then if the points form a line, and you don't know the context, which we don't here, we can connect them. The reason why I say and you don't know the context is that there are some contexts where even if the points form a line, it does not make sense to connect the points. So don't just do that automatically. We will talk more about that in a couple of days from now, though. So you're really clear on when do I connect the points, when do I not connect the points, okay? One misconception is that if they form a line, you always connect them, and that's not true, okay? It is, though, true that typically when we don't know the context, that we do connect the points if they make a line, okay? All right. Arrow or mapping diagram. So this is probably one you haven't seen before. And this basically consists of two bubbles. The bubble on the left is your independent variable. So this should be labeled. And this one is your dependent variable, just the same as ordered pairs or table of values. Independent on the left, dependent on the right. And what we do is we put all of the different x values or independent variables in that bubble and all of the different dependent ones on the right. And then we draw an arrow connecting the two, okay? So -2 is associated with 5 or mapped to 5. That's why it's sometimes called a mapping diagram. 1 is mapped to 2 or associated with 2. 4 is mapped to -1. Now, one thing that's important is that in these mapping diagrams, the arrows are unidirectional. They do not go in both directions. They always come out of the independent variable and point to the dependent variable. Yeah?
If there's a lot of values and you use this, could
Yeah.
you get really confusing?
Yeah, it could. But we can still use it. There are some circumstances where you see this. It's not one of the representations that we use very often, though. Okay? But we need to know what it means because we need to be able to interpret the connections between the two variables. Okay? Words. So we can also, oftentimes, if there is an association that we can recognize, describe it in words. Right? So I actually did that with height is associated with age. But here, can you guys see, maybe it's easier to look at the table of values, any sort of connection between the two variables that we can generalize? So when x is -2, y is 5. When x is 1, y is 2. When x is 4, y is -1. Can you guys recognize any sort of trend or pattern? Not pattern going this way between the x values or between the y values, but pattern going this way amongst the rows. Yeah?
The independent variable is increasing, whereas the dependent variable is decreasing.
Okay, so that's true. Independent is increasing, dependent is decreasing. But again, I want between the rows. Not this one's going up, this one's going down. So we've got -2 and 5, 1 and 2, 4 and -1. Yeah, what is it?
It goes up by 3.
What goes up by 3?
The independent variable.
Okay, that's true. Again, these go up by 3, these go down by 3. But that again is talking about one variable at a time. I want to know these two numbers, these two numbers, these two numbers. So I'll give you a hint. When I'm looking for some connection, I think about math operations. Okay? So I think about add, subtract, multiply, divide. Can I come up with any sort of connection there? If not, then I might think about some sort of exponential relation, like is something being squared or something being square rooted. I might go there. Yes? They all add to 3. Yes, that is the connection. Okay, so how do we describe it in words? What is the clear association between the two variables? The two variables have a sum of 3. Okay, this means if I know the value of one, I can figure out the value of the other. Right? With all of those other descriptions that you guys offered, although they're true, they don't really give me, I want more than that. I want a description where if I know one, I can figure out the other. So saying that one goes down by 3 and one goes up by 3, right? That doesn't necessarily tell me if I know that x is 0, what's y. Right? Whereas here, if I know, let's say x is 5, y has to be -2, because those are the two numbers that add to 3. Okay? The equation would be the variables have a sum, so x plus y of 3 equals 3. Okay? All right, any questions about this so far? Okay, so let's try some examples. We're going to basically spend the rest of the class switching representations. That's what we're going to practice, okay? And there are a few nuances that I'm going to add in as we go through these examples about some or more of the representations. So northern communities can be associated with the territories they are in. Consider the relation represented by this table. So here we've got a table of values, and by the way, values in a table do not always have to be numbers. And we are associating a community with the territory that it's in. Okay? So that's sort of a description of the relation. Communities are associated with a territory that they are in. Now, how could we represent this as a set of ordered pairs? Well, firstly, this is a set. So I'm going to start by opening up one of those. That tells someone that whatever I'm putting inside there is a set of values that all belong to the same relation. Okay? And I am going to make ordered pairs out of the community and the territory. Which value in the ordered pair should go first? The community or the territory? What do you think? Yeah, community. Yeah, exactly. Just because there's consistency, right? Whatever's on the left in the table of values should be on the left in the ordered pair. So I'm going to cheat a little bit and just use some abbreviations. I wouldn't do this if the table wasn't there as well, because otherwise people wouldn't know what my abbreviations mean. So I've got Hay River, Northwest Territories. So that's one ordered pair, comma. Iqaluit, Nunavut. There's another one. Nanisivik, Nunavut. Old Crow, Yukon. Whitehorse, Yukon. Yellowknife, Northwest Territories. And that's the end of the set, so I'm going to close off that bracket. Okay, so that's A. B, as an arrow diagram. Okay, so here's the thing about arrow diagrams. Firstly, again, we're going to have two bubbles. I'll do B up here. And similarly to the ordered pairs in the table, the community goes on the left and the territory goes on the right. Okay? And I'm going to put all the communities in here. Now, one thing that didn't come up on the first page about these arrow diagrams or mapping diagrams is this. If a value is repeated in the relation, we only put it in once into the mapping diagram. And all that happens is that there's either more than one arrow that comes out of it or more than one arrow that points to it. Okay? So if you look at all the communities, there aren't any repeats there, which makes sense. A community can't be in more than one territory. So I'm just going to put all of these in here. But the territories are repeated, right? So There's only 3 in total, and they're all repeated at least once, or at least twice, actually. So I'm just going to put them in once. And Yukon. Okay, and then when I'm creating my arrows, remember the arrows go from the community to the territory. This points to that. The Calalit points to none of it. This also points to none of it. Okay, Old Crow points to Yukon. White Horse points to Yukon. And Yellowknife points to Northwest Territories. Okay. So that's just one example of how we might be able to switch some representations. Okay, here's another one. Dog breeds, different dog breeds can be associated with their mean heights. Do you know what the word mean means? Yeah. Yeah, it's a type of average. Okay, there's actually 3 averages, mean, median, and mode. Typically when people talk about average, they're talking about the mean. Mean is when you add up all the values and divide by the number of things you added, right? And so that's often how like your marks are calculated. Not exactly though, because actually you guys have a weighted mean, meaning that each different item may be worth a different amount in terms of like, you know, one outcome is worth more than others kind of thing. But that's typically when people think about marks, they think about their average on a test or whatever. It's usually the mean. There are some instances, though, where median or mode are more useful. But most of the time, we talk about the mean when we talk about average. Okay? All right, so consider the relation represented by this graph and represent the relation as a table and as an arrow diagram. Okay, so firstly, this graph is a bar graph. Okay, does anyone know when it's useful to use bar graphs as opposed to like points instead? Yeah.
When you have a set of data, when you have a set of, when you have a group of things and you have a set amount of data about it.
Not exactly. So it's typically we use, yep.
Like if you have different X value things, like instead of it just being like all temperature, it's like different.
Okay, yeah, you're getting there. You're getting there. Yep. Did you want to add something? Quantity. Okay, so here's when we use a bar graph. It's firstly what we typically look for is only one of the variables is numeric. And then the other variable is usually a type of category, right? So if you think of the categories as different breeds of dogs, and then the numeric piece is what is their height, this is when we would use a bar graph, right? So another example is when, like, I know in elementary school, maybe you would have seen like surveys, who likes what flavor of ice cream? Right? And then you make a bar graph of who likes vanilla and who likes chocolate and who likes strawberry. So the categories there are the flavors of ice cream. Those are not numeric. And then the number is how many people like that flavor. That's typically when we use a bar graph over a point graph. Like a point and line graph, usually both values there are numeric in some way. Sometimes not exactly. Sometimes it's like one of them's time of day, where it does, of course, have a specific context, but they're still numeric values, okay? These ones are more categories. Okay, represent the relation as a table and as an arrow diagram. So as a table, if I'm making a table, let me switch back to black. Which of the 2 variables should go on the left? Which one should go here? Yeah.
Well, the independent variable should go on the left and the dependent.
So which one in this case should go on the left?
The mean of height should go on the right.
Yeah, so whatever's on the horizontal goes on the left. Dog breed. And it's really, really mechanical. You see something on the horizontal, it goes on the left. You see something on the vertical, it goes on the right. Mean height. Okay, so this one's like, don't think so hard. Just look at the graph, whatever's horizontal is on the left. Whatever's vertical is on the right. I'm going to put in the units here so that I don't have to put the units into every single value in my table of values. Okay, and then I'm just going to list, okay, what are my dog breeds? I've got the Afghan Hound, I've got the Chihuahua, and again, I'm abbreviating, the Corgi, the Golden Retriever, the German Shepherd, and the Malamute. Okay, and then I'm going to put in the mean height. What is the mean height of the Afghan Hound? Yeah.
75.
Good, it's 75. How did you know 75? Yeah.
It's in the middle, right in the middle of 60.
So first, it is in between 60 and 80. It's not right in the middle though. So, but what are we considering? Yeah. Yeah, it's in between 70 and 80. So before you start to pick apart a graph, really important to look at the scale on each axis. Okay, and I say each axis because if both axes are numeric, they often have different scales, right? So on one axis, axis, I should say, that's singular, each little square might represent 2, and on the other one it might represent 100. Okay, so be very hyper aware of that. Yeah, so this is 75. Okay, the Chihuahua is at 20. This Corgi's at 30. I think the Corgi is what the Queen likes to have, right? She has all these little Corgis running around. The Golden Retriever is at 60. This is also at 60, and that's the German Shepherd. And the Malamute is at 65. Okay, so there's our table of values. In the arrow diagram or mapping diagram, so I'm going to put my dog breeds on the left, and I'm going to put my mean height on the right in centimeters. Okay, so I don't have any repeat dog breeds. That wouldn't really make sense. You can just keep it, and I'll grab it in a sec. Okay. In terms of my mean heights, I do have a repeat. 60 comes up more than once, so I'm not going to put that in twice. The other thing that you should know, though, about these arrow diagrams is that if it makes sense to order the values, we do that. So what do I mean by that? If they're numeric, put them from least to greatest. If they're like months in the year, put them in order January to December. Don't just pick your favorite month and put that one first. Okay? So these, because they're numeric, I'm going to put them from least to greatest. So the smallest one is 20, then 30, then 60, and that's twice, so I'm not going to repeat that, 65, and 75. Okay? And then I'm going to draw my arrows. So, what's the first one? Afghan Hound, that's 75. Oh, maybe let's make that. There we go. The Chihuahua is 20. The Corgi is 30. Remember, the arrows only point in one direction. The German Retriever, or Golden Retriever rather, and German Shepherd are both 60. And then the Malamute is 65. Okay? All right. Questions about that? We're all good? Okay. All right, so we're going to look at another type of transformation in terms of how do we go from one representation to the other. And this is a really important one. This one is how do we take an equation and translate that into a graph? Okay. Now, as we learn more and more and more about those different families of functions that I spoke about earlier, you actually will not have to, this will be quite easy and quite efficient to do because you'll learn about their properties, and based on their properties, you'll figure out what the graph should look like. But at this point, all that we can do is use a table of values. Okay, so I've got an equation, y equals negative 4x plus 6. And I am going to try and come up with some points that would go on this graph. Now, when you are doing this, pick any values you want for x, and you can pick them randomly. But actually, there is a bit of a caveat there. So what do I mean by pick any? So, well, you could put 2, 6, 0, 1,000,000, pi, negative 1,000. Those are all values of x that you could pick. You wouldn't want to pick some of those, though, knowing that this has to go onto this graph. And if you look at the x values that are visible on this graph, they go from negative 10 to 10. So I'm not going to pick 1,000,000 because although it would go on my table, I'm not going to be able to graph that. That would be like, I don't know, somewhere beyond the CT center. Not practical, okay? So, you know, use the grid that you're given to sort of dictate what values you're going to put in for x. Okay, I'm going to do like -2, -1, and I typically go in order. So I may not do everyone, I may do every other one, but I follow a pattern in my x values. You don't have to, though. You could pick -2, 5, 3, 7, 0 if you want. Okay, it doesn't matter. The reason why I like to go in order is because it might help me to figure out what type of relation I'm dealing with, what pattern is going on, if I see a pattern in the y values as well. Okay, but you don't have to do that. Now, to figure out the y values, I'm going to use this equation and the specific x value to get the y value that's associated with that. So, for example, if x is -2, y is -4 times x plus 6. So this y value is going to be -4 times -2 plus 6. The next one is going to be -4 times -1 plus 6. I'm subbing in my x value to find a specific y value. This one's going to be -4 times 0 plus 6. This one's going to be -4 times 1 plus 6. And this will be -4 times 2 plus 6. Okay, and then either use a calculator or you probably could do this in your head to figure out the y value. So this is like 8 plus 6 is 14. Okay, -4, right? +4 plus 6 is 10. 0 plus 6 is 6. -4 plus 6 is 2. And -8 plus 6 is -2. Okay, so we can clearly see, actually, that there is a pattern going in here on here. Every time x increases by 1, y decreases by 4. Okay, and we'll learn more about that next week as well when we talk about how do we tell if something is specifically a linear relation. This is actually what we're looking for. Okay, but more on that later. And then we're just going to plot the points. So when x is -2, now 14 is off the page, right? It's not so far off the page, though, that I couldn't sort of estimate where it is. So that's okay. 14's probably around there. If it's not like way off, you don't want to do this if the y value is like 40. Because typically, firstly, it's going to be, you know, on the ceiling. And secondly, you will lose accuracy if it's way above your highest y value. But if it's just 4 above, that's okay. We can plot that. So when x is -2, y is all the way at 14. When x is -1, y is at 10. When x is 0, y is at 6. When x is 1, y is at 2. When x is 2, y is at -2. Okay, and then if they form a line, connect them. And please use a ruler. Like, I'm not doing that because of my smartboard, but they should be straight lines. You don't want like a wonky, this is not even that good, right? On my old smartboard, I think I could put a meter stick up there. I think on this one, It's like super reactive, so let's see what happens. Oh no. Oh yeah, see, the pen is like, oh my goodness, look at that. It's got a mind of its own when I put that meter stick. All right, so that's not gonna work for me. Don't do that, but you guys aren't working on this, so you should be able to use a ruler. I'll put that back in there. There we go. And also put arrows on the end of each, on the ends of the line, because this actually keeps going, right? We're just seeing a snapshot of it within this grid, but this is a line that goes on infinitely. So we show that with arrows on the end. Okay? All right, questions? Yes? Yeah. So here's what I want you guys to do. I have 8 equations here. I want you to pick 4 of them. Any 4 you want. And you can see that there's one table of values here and a graph. And if you go on to the next page, there are 3 more. And I want you to graph them. Okay? So we're going to do that next. The other thing, though, is because when you're done that, you can start working on your homework. The homework today is not in the textbook. It's actually in the other grade 10 textbook because I just think that one does this section better. So what I did is on D2L, I just took a picture of what I want you to do, and I've linked to it in my announcement for today. It's right here. And it'll take a second to load probably, but there's just pictures of the questions, and the last page is the answer key, okay? You don't have to do all of them, so I think I wrote in my announcement what I want you to do, but they're all there. And when you are done doing your 4 graphs, you can start working on that, please, okay? Okay, let me turn off the recording.